topic list. So we've got, again, this is test 12. We're looking at 9.2, 9.3, and then 10.1 through 10.4 pretty much. We only did it as 3 sections, if you remember. Okay, we did it as 3 sections really, but it's actually 4 sections in your book. Okay, 10.1 through 10.4. 10.2 and 10.4 we did together. Please notice that there are certain things that are in your text that I don't go over, and it's not a matter of like what you're capable of understanding. It's honestly sometimes what I find interesting. If I find that something's really theoretical and kind of boring, I don't usually go into crazy detail. If you are interested in physics and you study more physics, trust me, you will go over those kinds of things that maybe I do cut out. But I like to teach things that are application-based that you can, think about some real-life relationship with. So in 10.2 and 10.4, I cut out a good amount of material. So if you're looking at your text and you like to use your text to study, just please be cognizant of that. So when you're studying in 10.2 and 10.4, you're not like, oh my God, we never went over this and it's in the textbook. That means it's not in the text. Okay? So use your notes as a baseline for that. 10.3 was where your math came from, if you recall. The math really came from calorimetry. It came from looking at how much heat was necessary to change the phase of a substance or the temperature of a substance, or, for example, a calorimetry balance, which I think I gave you as a homework problem. I don't think we did it in class. And a calorimetry balance is like when you take a hot piece of iron and drop it in water. If you can see the change in temperature of water, you could determine how much the iron changed in temperature. Or you could determine the mass of the iron based on how much temperature changed in water. And we'll do one of those today, okay? We'll do one today. And I have to remind the other class to watch this video, because I don't think I did one of these kinds of problems in the other class during the interview. And they reviewed yesterday, unfortunately.
Is this more a theoretical test than a math test?
No, it's both.
50-50?
Yeah, I'd say half and half. I think it's probably going to only be like a 40-point test. Not the same as the last one, but half and half in math and theory. So let's start first, though. I was just giving you an overview of chapter 10 there. Let's start with 9.2 and 9.3. In 9.2, we talked about fluids. We talked specifically in 9.1 about buoyancy. That's on your last test. So luckily, that's kind of, last year, they had all of this on the last test. 9.1, 9.2, and 9.3, and all of chapter 10. So it was a much tougher test last year because 9.1 was included. That was a really pretty tough section a lot of you struggled with in the last test. So you don't have as difficult of math at hand on this test, except for 10.3 if you find that difficult. 9.2 and 9.3, the math is like super easy. You did it with your lab. The video lab that you submitted, that most of you submitted, some still have to submit that video lab. It's way overdue at this point. Please get it to me if not, if you haven't done so. But 9.2 and 9.3 is about Bernoulli's principle. It's about pressure and Pascal's principle. It's about the continuity equation. So there's a lot of stuff going on in these sections here, but the math involved is really rather straightforward. We'll start with the first part with math. We talked about pressure, and pressure being force over area. Talked about pressure being force over area. And the simple example we gave was the concept of like if you take a pin and you poke a balloon in a pop. But if you took like 100 pins on a board, and you take that balloon and you try to pop it on all 100 pins at the same time, it will not pop. It will not pop. And you wouldn't believe that actually. If you came to that physics show, you would have seen it. And the guy on that physics show, he decided to put like 200 nails on a board, and he was literally taking a balloon and trying to pop it and hitting it. It would not pop. You could see the force of it. The balloon was bending, and it wasn't popping. Because the force that the nail was providing was distributed over like 40 nails. So it was 1/40th of the pressure that would be exerted over one single nail. So pressure being force over area. So the less area you have, the more pressure you have. Another simple example to remember is if you stand on one foot. What are you doing? You're halving the area, aren't you? So you're doubling the pressure on that foot. It's the same amount of force. The force is just the weight of the person. So if I'm thinking about a person standing up, now it's just Fg over A, the weight of the person over the area. But if I suddenly pick up one foot, I've halved the area. Well, that's what I've done to my formula, if you think about that, right? By halving the area, since it's indirectly related to the pressure, I'm doubling the pressure, really. Dividing by half is the same thing as multiplying by 2. Okay, so I'm really doubling the pressure by halving the area. We took this concept and ran with it. And we we went over the idea of Pascal's principle, and some of you did this for extra credit. We talked about this was the unbreakable egg extra credit. I think Zoe, you did this one, right? Yeah.
I did it.
Did you do it also? I didn't get to your name in the alphabet. Isn't that funny? Because you're cats. So I'm going through your Dropbox folders actually last period. I saw a few. This was the unbreakable egg example. And the concept was that the pressure in a closed volume or a closed system is equally distributed throughout the actual body of that volume. So the egg, when squeezed, feels a certain amount of pressure on it. That pressure is exerted backward equally to all the walls of the egg, keeping it in a state of equilibrium, actually.
I have a funny story.
Yeah.
The other day at lunch, we asked the lady if we could borrow an egg and just size up her thing, and Joe was holding it. I was like, oh, if you apply pressure,
will break. Actually, oh really? Crush guitar player.
No, so-
no, Joe.
We
and then I was
we
just
have a
like,
video.
not too hard.
Yeah, if you break one, if you put enough pressure on one spot, it'll always break. You have to do it in you did it indoors and you showed it and they didn't crack it after you showed one
How
spot.
do you know if you're doing it like?
So Theo,
You take the egg and
I have a video.
yeah. So Theo, look, show Mr. L. Find it funny, or you don't have to show him later. But Theo and I, so Theo was doing it really hard. We couldn't.
Do you have it in the video?
He has it. I don't know if he submitted
I
it.
haven't
It's on
seen it
his.
yet.
But
I
it's
can
and
see
then I add my. You should add it. And then I add my hand onto it, and we both push really hard, and it's still
It's
not
still
working. And then at some point, we're both just go crazy, and then it breaks.
Yeah.
It just goes everywhere.
I mean, there's
It
obviously
gets
some
splattered all over the
structural limit to the amount of force you can really apply. So it's not unbreakable, but the concept behind it is pretty cool.
Be careful, by the way. You remember you're supposed to edit it.
Did you find my
Next
tear
box.
names?
that?
Did you find my tear names?
Oh, yeah.
My tear names.
I'll just take out this.
No, it wasn't. I don't even have. I thought I had the
Did
folders.
you say it was? Wait, what's?
I used to have some of the old folders from my students in the past,
What about my two?
but I had like 2 years ago. I had last year, so I have Elliot. Wow, see, Anthony. I have your brothers from last. No, your
2
brother was
years.
senior last year. That was 2 years ago. I don't know this. Who was juniors last year?
You have Jack Morgan, I was right, wasn't in your class.
No,
You
it would
probably
be the
have,
seniors
but-
from this year. I had theirs still.
Oh.
What did you do?
My team just made a fool of himself. It was hysterical. And at the end, to prove that the egg was not raw, he cracked it and drank the egg. Yeah, like that, and made
And a dinosaur suit.
in a dinosaur suit the whole time. It was hysterical. It was just like one of those things. Mike was
Did
like,
you
Mike.
did you give him extra credit?
No, I make it. Yeah, I got 2 points normal. Like extra, but not extra. But he was creative, you know. It's not. I don't know why he did it. It made no sense in that sense. The dinosaur suit part, but the cracking of the egg afterwards to prove it wasn't hard boiled. What? No, that's what they asked me. I said I have last year's class's Dropbox folders on my home computer. So I don't have the ones from 2 years ago or 3 years ago. I think I just started cleaning them up because it was just all of your folders in Dropbox is almost 15 gigs worth of space. So my Dropbox fills up quick. So at home I put them on the home computer.
Could we go over the pressure spread? I don't really.
Yeah. So this is the idea that when you have a closed container. So we applied it to a hydraulic press, Frank, like this. We talked about, okay, well, what if you have a machine that in one section has a small cross-sectional area? That's like this section on the right over here. And if you apply a certain amount of force to that area, it'll magnify the force. It's a mechanical advantage. The force felt over here is much greater. Well, why is that? And it comes from this principle. Because pressure is force over area. So you can do this. Do you remember this from class? Okay, this allowed us to take a look and say, all right, you know what? If I change the area, it changes the amount of force. So if I go ahead and think about this on this end, let's say that area 1 is 2 square meters, and let's say that area 2 is 8 square meters. What's the factor of change there? What's the factor of change? Come on, it's simple, let's go. Factor of change, 2 to 8. 2 to 8. 4. Right? You should know this by now, guys. Again, I'm not asking for the amount of increase. The answer was not 6. Okay, so to go from 2 square meters to 8 square meters, your factor of change is 4. So what's your force going to change by? 4. So if I apply force on this end, so let's draw a force vector, please. I apply a force, FP, some push, of 50 newtons. Okay, if that force I apply is 50 newtons, in my area when I apply a factor of 4, the force will go up by a factor of 4 as well. So the force that's actually felt on the other side of this hydraulic press, pushing up on this piston, this force will be 200 newtons. Okay, you can call them F1 and F2. I called it FP over here. Let me just make this look a little bit nicer.
So which one is, so F1 is 2, or?
No, it doesn't matter. Just one location is 1, one location is 2. It's whatever you want to call it, Katie. I could call the left side of this hydraulic press F1 and A1, and then over here this would be F2 and A2, as long as they are consistent. The force applied at that area needs to have the same subscript. These have to both be subscripts of 2, and then all you have to do is plug it into the formula. And you'll see that 200 divided by 8 is the same thing as 50 divided by 2. They're both 25, aren't they? So these fractions are the same. The relationship here is proportional. Okay? If I double the area, I double the force. If I triple the area, I triple the force. So when you're working on a car, and a car weighs 2,000 pounds, the car is usually on a wide area lift. The other end is a small piston pushing down on it. It's a hydraulic press. And usually, you just turn on a motor, and the motor pushes down with very little force on the piston, and the car raises up. But here's the thing. This is a fun fact. Maybe you should write this down. It's kind of one of those questions I probably ask you. You have to think about it more on the test, but I'll give you a hint at it now. The smaller piston on this right side goes down a lot further than this piston rises up. Again, when I push down on the smaller piston on one end, the bigger side doesn't move up as far, not nearly. So as a result, to move up a car, say to lift a car 2 feet off the ground, you might have to push the piston 8 feet. What's the factor of change there again? 8 to 2 instead of 8 to 4. If I want to lift a car a foot off the ground, I need to push down on the piston 4 feet. Okay? So that factor of increase also affects how far I have to apply F1 for. Yeah, my force is only 50 newtons, but I have to push down 4 feet just to raise the car up 1 foot.
Wait, so what's the ratio?
It's still 1 to 4. It's whatever the ratio of the areas is. See, the ratio of the areas, 2 to 8 is 1 to 4. So that means that if I push this one down 4 feet, the car only goes up 1 foot. But the force I push is only 50 newtons. That's the advantage. You don't have to put a lot of effort in, but you have to put that effort in over a longer distance. That's how a ramp works. You know that, right? Physically, think about your simple machines. A ramp on the end of a truck. So do you want to lift a couch onto the truck, or do you want to put it on a dolly and wheel it up the ramp? So much easier, right? You wheel it up the ramp, it's a longer distance. You're wheeling it. So you're pushing on the couch for a longer distance, as opposed to lifting at a shorter distance but with more force. Would you rather push with less force over a longer distance, or push with more force over a shorter distance? It's the age-old question, and you all know this. Hey, come out to the car and help me with the groceries. Oh, come on, Mom. No, come out and help me. You go out to the car, and it's like 16 bags of groceries. All right, Mom, I got 8 on one arm, 8 on the other, and I'll make it to the door. Right?
That's the truth.
It's a lot of force over a small distance to the door, as opposed to less force and how many times you have to make the trip over like 4 times the distance. It's the exact same thing, really. It's a mechanical advantage. So you're applying this force of 50 newtons over 4 feet, and it only raises the car up 1 foot. And that's the reasoning behind the mechanical advantage. All right, that's pretty much 9.2. Look at 9.2 real quick. Tell me real quick. Somebody pull up your notes. Say again? Oh, that was the other part. Thanks, Ant. See? Pressure as a function of depth. Let's talk about this. We've got pressure total equals absolute pressure plus density times gravity times depth. Write yourself a note right now if you didn't remember that. H is depth. We call it H because it's the height of water on top of the object, which is what depth is. Okay, remember, it is depth. Some people in their video use the word debt, like the economic debt. The word is depth, D-E-P-T-H, depth. Anyhow, so let's talk about this for a second. A lot of you did, I shouldn't say a lot, I'd say about half the class did a good job of explaining this in the video, what absolute atmospheric pressures are going to use absolute zero. A lot of you did a great job explaining these. Why were these easy to explain? Think about your video. Why was it easy to explain rho GH? Really easy to explain them. Why? You all just explained it really well, but don't know why it was easy? Why was it like 10? It took most of you 10, 30, 20 seconds to explain those real simply.
Because all you had to do was grab the pressure slider, and then you could micro the pressure gauge, and there was just the slider so you could adjust gravity and density and
And what was your conclusion? They were all what? Fill in the blank. They're all
direct
to the?
pressure.
Yeah, they're all directly related to the gauge pressure, the pressure felt underwater. If gravity is more, well, that means that the water weighing down on the object is heavier. If the height of the fluid or the depth is more, it means there's physically more water weighing down. It's heavier. If the density of the fluid is greater, it means it's heavier. So in the end, these three are all directly related because the water on top of the object gets heavier pretty much. They're all directly related, yes.
Is PGH the gauge
Rho
pressure?
gauge.
Oh, rho gauge, is that the gauge pressure?
That is. Remember, so let's break this down into pieces. We've got gauge pressure, not gauge pressure, just so you guys know. So many funny pronunciations in these videos, let me tell you. Gauge pressure, atmospheric pressure, and then total pressure. And if you think about it physically, it makes so much sense. Here's the water. Here's the object in the water. Here's the surface or the floor, whatever. So here's the atmosphere, right? The atmosphere applies pressure down on the water. The water applies pressure down on the object. Well, look, this is atmospheric pressure. This is the water pushing down with gauge pressure. How do I find the total pressure? God bless you. How do I find the total pressure if they're both pushing down? I add them together. The physics behind it makes sense. And some groups really did, or some people did a great job explaining this in their Lab 17 video. Others did not. Others of you said, I turn off the atmospheric pressure, it's less, you know? We didn't really talk about this relationship here. And that's physically what's happening. Atmosphere pushing down on the water. Water, in turn, pushing down on the object. So the atmosphere and the gauge pressure in the water are both pushing down. If they're both pushing down, what do you do to them? You sum the pressures, like you sum the forces. If two forces are pushing down an object, you would say the overall force is the sum of those two forces. If they were pushing against each other, you would sum them with one positive and one negative. Well, here they're both pushing down, so just add those two things together. Atmospheric pressure, where do you find it? Where do you find P0?
Is it given in the table?
Yes, it's on your formula sheet at the very bottom. It says P0 equals 1 times 10 to the 5th pascals. A lot of books are going to write 101.3 kilopascals. And if you think about this physically, this is the same thing as 1 times 10 to the 5th pascals. If I move the decimal 2 spots over, that gives me 10 to the 2, and then kilo is 10 to the 3, so 10 to the 2 and 10 to the 3 is where your formula sheet comes from. It comes up with 1 times 10 to the 5th. Okay, but a lot of the books are going to write it as 101.3 kilopascals. If you move it over 2 spots, it becomes 1 times 10 to the 2. Getting rid of kilo makes it 1 times 10 to the 5. Okay, but just so you know, that's where it's from. Does this affect, or does the pressure change if the object is a different object? No, it does not. Good, Katie. This is really, it's kind of beautiful to think about. The object itself does not impact how much pressure is exerted on it. The shape of the object itself has no effect on the amount of pressure on it. But we've talked so much about the fact that pressure is force over area. Yet, the area is not involved. It's just the depth in the water. And that comes from the derivation of this, if you remember. You don't have to prove this, but you should understand this and know this. We derived this formula, and in the formula, we canceled area with LW. We had volume equals LWH, the volume of the water, LWH, LW canceled with A. There's nothing to do with the actual object here. It's just its location underwater. That's important. The continuity equation and Bernoulli's principle. The continuity equation we started with was this. What does V stand for?
Velocity.
Velocity. Not to be confused with volume. Or voltage, obviously. I'm hoping voltage here, right? I can see it being confused with volume, but definitely not voltage. What does this tell me? In your own words, please. Don't just regurgitate the continuity equation or the theorem. What does this tell you in your own words? A1V1 equals A2V2. Or give me an example of where you see this principle or this theory at work. Either an explanation. Emma, go ahead.
Well, for the lab that we did, like when you decrease the area of the pipes, the water will move faster through, so the velocity will increase when the area is smaller.
So how are area and velocity related? Inversely related. Very good. This concept here, because AV is a constant, it's the volumetric flow rate. The volumetric flow rate is a constant. So these two have to equal some constant number, some value, right? So let's say I know the second area is 5 square meters, and the velocity at that point is 2 meters per second. Well, that's just 10. Agreed? That's all that is 10. And my units, by the way, are cubic meters per second. That's why it's a volumetric flow rate, cubic meters. Well, if that's the case, and I've got a velocity on this side, let's say I triple the velocity to make it 6 meters per second. If I triple the velocity, I have to reduce the area by a factor of 3. If I make my velocity go up by a factor of 3, area has to go down by a factor of 3. So this would be just 5/3 meters squared. Okay? Again, if one thing goes up by a factor, the other thing has to go down by the same factor. That's what the continuity equation tells us. What's besides a pipe flow, which you see, the easy example in class I gave was taking a garden hose and putting your thumb over the end of it. You've all seen it, just remember that. You put your thumb over the end of the hose, the water speeds up. Less area, higher velocity. Okay? Bernoulli's principle, and I didn't, by the way, there is Bernoulli's equation in your book as well. I did not go over that. You can look at it if you're interested. What it does is it accounts for height. Because if you think about it, if water's flowing down a pipe and there's gravity pushing down also, well then things change. We've been talking about things that are horizontal so far. But Bernoulli's principle tells us something that's related to this. And it tells us that the pressure and the velocity are indirectly related to each other also. And let's go over that real quick. Let's do that with a diagram. So you've got some sort of a flow of water or fluid in a garden hose. Here's the end of it. And suddenly you cover up the end of it so that only the water can flow out this way. Okay, so normally the water is flowing down the entire pipe, and then suddenly all this water has to converge to this exit. Okay, right here. Well, here's what's happening. We talked already about the velocity increase, and that's great. But the pressure is also involved. And if we think about this, to go from a low velocity to a high velocity, when you have a change in velocity, what must you have? I'm going through this proof again. It's a simple theoretical proof. Change in velocity is caused by what? Yes, but more basic, fundamental things. Velocity change indicates the system must be doing what? What is the word? Accelerating. Remember, acceleration is defined as change in velocity over time. So that means that there must be some acceleration to the right. Agreed so far? If there's acceleration to the right, there must be Newton's law. F equals ma. If you have acceleration, you have force. So there's a net force to the right. If there's a net force to the right, what equals force over area? What equals force over area? Pressure. So that means the pressure differential must be to the right, which means you have a high pressure here and a low pressure out here. That's the reason for this whole thing. Again, low velocity, high velocity means it must be accelerating this way, which means the net force is this way, which means the net pressure is this way. So you have a high pressure location and a low pressure location. So automatically the fluid gets forced outward. Okay, so again, low velocity is higher pressure, high velocity is lower pressure. You're technically, by putting your thumb over the end, you're building up pressure in the garden hose. And then afterward, when the actual water shoots out of the end of the garden hose, it comes out at a higher velocity, it's lower pressure. The pressure has been reduced. Did you know that when you drink from a straw, anything with a straw in it, you know what you're doing?
Oh yeah, you create pressure in the straw, but it's not you sucking on it, it's like your tongue or something.
It has to do with reducing.
That's why you can't like really watch.
Have you seen that video? Okay, there's an awesome video on YouTube. You gotta watch it. This guy tries to prove the longest straw that can physically be used on Earth, and it's actually physically a number. It's not like you can say like, oh, I can pull on the straw harder than somebody else. You know what I mean? I can provide more pressure to pull the fluid up. It's like something like 10 meters or something ridiculous. But the reason is this: to get fluid to flow up a straw, you're creating a pressure differential. By actually sucking in your mouth, like through a straw, you're lowering the pressure in your mouth by creating almost like a vacuum in your mouth. Lower pressure in your mouth, higher pressure out there, higher pressure pushes to lower pressure. It's just Bernoulli's principle, that's all it is with a straw. So the pressure in the container is a higher value than in your mouth, so the fluid wants to go to lower pressure. It shoots up the straw. It's like energy. Higher potential energy, lower. Doesn't the object want to always fall to lower potential energy? Same thing. So when you're doing that, you're creating a lower pressure in your mouth, which causes the fluid to flow up the straw. I only learned that actually. I mean, I knew the theory, but I saw that video like maybe a month ago, and that's when it really clicked for me what was happening. So if you think about this, to cause the fluid to flow up the actual straw, you can only create so much differential pressure in your mouth to actually have that happen. It's impossible because the volume of your mouth is a certain amount. And you keep like thinking like, you just keep pulling air in, but at a certain value, I think it actually has to do with atmospheric pressure. There's a certain limitation toward it. But if you YouTube that actually as a term, longest straw possible, it'll come up. All right, that's chapter 9.
But you know the things that squirt water out really fast. Do they use that?
Like at a dentist, like the water picks, or you mean like a water gun?
No, you know the thing that if you gotta clean like a big table and it sprays.
Oh, like a nozzle. The word's a nozzle.
Yeah.
You put it on the end of the hose. You put it on. You can spray
water
something.
that goes really fast. Do they use like the idea of like?
It's exactly what it uses. Absolutely. That's how firefighters get to higher windows. They have a tapered nozzle at the end. When they increase the area, the water comes out slower. They close it off to make it a really fine point, and the water shoots much further. It's the exact same principle as a nozzle on the end of a hose. You spray like you want to spray your plants. If you want misty spray, it's a lot of area. It comes out slower. If you want really high velocity, go further, you change that. Take a 3-minute break. We'll come back and finish this. So, in section 10-1, we started by talking about temperature scales, and what actual temperature is measured by. What do we say temperature really is? What is temperature really a measurement of? Who remembers? The movement of the molecules. Very good, class. It's the kinetic energy of the molecules. Specifically in gases, it's very obvious because gas particles are moving. It's very obvious and it's easy to see that. It's not easy to see that, but it's solid. You would not say that these particles are moving, would you? Honestly, no. You definitely not say that. But they are vibrating at some frequency, and the actual amount that they're moving, or the rate at which they're moving, will indicate the temperature of the actual object. Let's think about the concept of absolute zero. Let's talk about this for a second, because I feel like either A, maybe you didn't learn it. Did you learn it in chemistry or not? The concept?
You can't ask.
Absolutely.
You used Kelvin in your measurement, didn't you?
It was so long ago.
That's really funny here.
It's just
Let's-
a blur.
yeah.
Scariness.
So let's talk about it for a little bit, because I feel like it just did not click, it did not sit well with people. So the concept of absolute zero is this. The lowest temperature possible means the absence of any motion of molecules completely. That's because the measurement of temperature is the motion of the molecules. So to get an absolute zero, you'd have to have the cease of movement of molecules, and that's very difficult. It's actually impossible. Scientists have gotten very close to it, but the theoretical approach is that there's a limit to it. And you're going to learn about limits next year in pre-calculus. You may have learned about limits, no, not algebra 2, pre-calculus. Actually, no. Did you learn about rational functions this year in algebra 2? Did you learn about horizontal asymptotes?
Yeah.
You learned about logarithms and stuff?
Yeah.
Horizontal asymptotes, right? Okay. So, you know what the absolute zero scale is? It's a horizontal asymptote. You can never get to zero, but you can approach it. You can get closer and closer and closer and closer to absolute zero, similar to a half-life of an element. every time it halves, it gets closer to zero, but it never gets there, because you're just having it over and over. Well, that's the same concept. The reason behind it, the easy, simple explanation is, think about how you cool something down. How do you cool something down?
When something colder than itself.
Exactly. You put it in something colder than itself. Well, how can you get something to absolute zero? The container itself would have to be less than absolute zero. But by definition, absolute zero is the lowest you can get to, so it makes that a limiting function. You can never really get there. Now, the concept behind it mathematically is simply this. Your scales are horizontal. You guys have learned a ton this year in your Algebra 2 class about horizontal and vertical shifting, about transformations of graphs. You've applied them to your parabolas. You do the absolute value function this year, the V? Okay, you've talked about horizontal and vertical shifts. These scales are simply a horizontal shift. What was your formula for Kelvin? How do you find the temperature in Kelvin? Either look at your formula sheet or look at your notes. What do you have for Kelvin?
Isn't it Celsius plus 273?
I think on your formula sheet I just put 273 actually. So it's pretty much saying this. If you want to find out what the temperature is in Kelvin, just shift the Celsius scale up 273 degrees. So if it's 0 Celsius out today, first of all, what is 0 Celsius? We should know this number. Should we know? Freezing point of water, H2O. So 0 Celsius is freezing for us. Well, plug in 0, you get 273 for Kelvin. So 0 Celsius is not very close to 0 Kelvin at all. It's 273 Kelvin. So what we consider to be freezing is 273 degrees higher than absolute zero. So try to like just even think about that, conceptualize how cold absolute zero must be. It must be absurdly cold because we think of 0 Celsius as very cold, right, as humans? It's because temperature is all relative. Temperature is relative. We've said that many times. Yeah, right.
What do you think is like the coldest, like, I don't know,
Well,
temperature that like labs and scientists?
they've been able to get certain metals down to temperatures that are like 1 or 2 kelvins, and they act as superconductors, and they exhibit no resistance electrically.
But like air-wise or gas-wise, you know?
The thing is this: once you cool down enough, the gas becomes a liquid, and then, or it sublimes, maybe it jumps the stage. But yeah, you immediately have condensation, and then you have solidification or fusion.
Is it like dangerous to make like liquid nitrogen and then make liquid nitrogen into like a solid? Is that like very dangerous?
To make solid out of nitrogen, I think it's absurdly close to absolute zero. Look at the table I have has nitrogen, I think, listed as it. I don't know. I mean, certain gases are just volatile and they react very irregularly or unpredictably. But changing the phase of an object changes the amount of energy, so it does do things. And it does probably have impacts like that. But specifically with this, I want to just focus on the concept that it's a shift in temperature scales. If I were an alien from another planet, did I go over this example with you?
No.
Alright, so I'm from Mars. Oh no, Mars is too easy. I'm from a planet, whatever, another galaxy, and I decide to come to your planet and visit. And I say to you this, right? I land on a summer day, and I say to you, it is so cold on this planet. I'm freezing right now. It's hot. It's like 98 degrees out, okay? You're on the beach, it's hot as hell. And I'm sitting there, I'm with my alien, and I say, it is so cold on this planet. What can you conclude?
That it's really hot in there, planet.
Exactly. That their planet is very hot, and their body temperature runs much higher, so as a result, our planet feels cold. You see what I'm saying here? Okay? Now, the other part about temperature, we talked about this with conduction, convection, and radiation, was the temperature. It's like they're all right outside this window. Right? Yesterday, I was so annoyed. My whole entire class during math, Algebra 2, there was a jackhammer going on the entire time, right outside the window. I was losing it, and I was like, so frustrated. Anyway, so the conductive nature of metal allows heat to flow out of my hand into the metal very easily. But wood is actually a thermal insulator, so the heat does not flow out easily. It also has to do with the temperature difference. If the temperature difference is great, heat wants to flow much easier. The heat flux is higher. Okay, it's higher. The three modes of, we talked about conduction, convection, radiation. Conduction, what does that involve? What does conduction involve? How does heat travel or transfer through conduction? I'll give you a hint. Touching the wall is conduction, but blowing a fan over my hand is not conduction.
By touch.
Through contact, very good, through touch. That's why a double pane window acts as an insulator. The air in the inside of the room touches the glass touches the gas in the inside, the gas in the inside touches the next glass, so it's conduction that's limiting the flow of heat because the gas in the inside of a double pane window acts as a thermal barrier. It acts as an insulator. Katie?
Isn't everything technically conduction?
Yes, but that's assuming that everything is static. The minute a fluid is no longer just touching the wall but flowing, it's convection. That's the difference. So yes, the air in the room touching this window, touching this board is transferring energy through conduction for sure. But if I go like this, now I'm transferring energy through convection because the fluid is flowing over the surface. Okay? Yeah, convection oven does exactly that. It provides heat at the bottom, right? The heat at the bottom wants to rise, and the fluid, the gas, the fluid starts to flow. And it flows in a convective nature, so it provides heat transfer. It's the same thing as the air conditioners. The cold air comes in, and it falls to the ground. The hot air rises up, and the air conditioner pulls the hot air out of the room, and it pushes it out. So that's through contact. Convection is the second type. And this has to do with fluid flow on a surface. Okay, that's specifically fluid flowing on a surface. So if I had liquid nitrogen running through pipes over a CPU of a computer, I do that because the liquid nitrogen is so cold, it absorbs the heat from the CPU and it reduces the temperature of the computer, allowing the computer to process faster. That is convection, actually, because it's fluid flowing. Even though it's a pipe, it's conduction through the pipe walls, but the fluid flowing is actually convection. That's usually also a thermodynamic cycle and process. If you like cars and you like things about combustion, thermodynamics is a topic you want to study for that. It's a chapter in your book. I don't ever really get to thermo. I talk about it, I allude to it, but I don't talk about it. I took a whole course in college, an entire year on thermodynamics. It's like simplified to one chapter in your book. Frank?
Will we have to know specific examples of both? Real world examples.
You should definitely be able to, like, if I gave you an example, understand what it is. If I said, cooling down this by this process is example of convection, conduction, radiation, you know what I mean? Something like that you should be able to identify. I don't know, I mean, being able to provide an example is always good. So if I wanted to provide an example of conduction, anything you touch that's hot is conduction. Anything that has any air or fluid flowing is convection. So it's very easy to come up with examples. Radiation would be the tougher one. Radiation involves energy. Okay, change in energy. Let's talk about that for a second. I think we ran out of time at the end of class when we were talking about this. Radiation involves energy transfer. But, oops, that's an S in there. But because energy transfer and conservation of energy is analogous to our heat, we know that when energy transfers, heat also transfers. So radiation are things where there's a hot body and it's physically radiating energy. You do it every day. You are a personal radiator. You are physically a radiator, actually. Okay? Your body radiates energy. Your body undergoes exothermic reactions all the time. You consume food. Food has energy. That energy is transferred, and then you radiate that energy. Now, obviously, there are limitations to this radiation concept, but the concept itself is pretty straightforward because of the fact you think about radiating energy outward as energy decreasing from your body, thus increasing the temperature around you. Have you ever been in an elevator with 10 people and you're in there for a little while, or you're in a room that's packed out? What happens to the temperature of the room? It's hotter because everybody's literally radiating energy. That's how the sun radiates energy toward the earth. The last thing we have several formulas. They are as follows. Now, these three formulas all involve Q. Q is measured in joules. Joules are energy. So here we're talking about the energy necessary to either A, change a phase, B, change the temperature. One of those two things. So, we did an example. We did actually two examples. We talked about one and did one, and then you did one for homework of an object or a substance changing temperature and phase. I will theoretically talk about it. I'm not going to do the math right now for it. I want to do the math of a separate kind of example. So theoretically, let's say that, let's say we have H2O, just because I have these memorized, I'm using H2O here. If I had my table in front of me, I could use lead or another material. But let's say I have H2O, and I'm saying H2O on purpose. I'm not saying ice, water, or steam. Because if I say that, then it gives something away, right? So I have H2O at negative 30 degrees Celsius, and I want that to go up to 80 degrees Celsius. In the process of going from negative 30 to 80, what happens? Go. Who can tell me? What happens? Run me through the process. Katie.
It changes, there's a phase change first. Or no, it goes from a solid.
So it starts as a solid. Start with that, Katie. Go ahead. So we have solid.
It starts as a solid.
What's the temperature when it's a solid?
It would be negative 30 up until 0 degrees.
Up until it gets to 0.
Yeah.
So it takes a lot of energy to change the temperature. To go from a solid, and it's still a solid at 0. Again, you have to change the temperature 30 degrees to start. Katie, what formula would you use when you have a change in temperature? Very good. Now, somebody else for the second part. So the ice goes from negative 30 to 0. It's ice. I can say that now because it was solid. What happens at 0? What happens at 0? Joe?
Well, then it starts to melt.
Until it becomes all
Liquid.
liquid. So we have a what? What do we call that? Phase change. So this is Q, and I'll put phase here. And it goes from solid to liquid. What's the temperature still, though, Joe?
Well, temperature's still 0.
Yeah. Technically, it's still 0 the whole time. All it does is change phase. Now, if there's a phase change, which formula do I use? If there's a phase change. There's a phase change. Which formula? You have one of two options. It's not Q equals MC delta T, I'll tell you that. Is it LF or LV in this case? That?
LF,
Why?
because that's fusion, and fusion is from solid to liquid.
Good. F stands for fusion. Fusion is solid to liquid or liquid back to solid. V stands for vaporization. That's liquid to gas or gas back to liquid. So this is going to be used, oops, where are we? Q for phase, I'll write the formula up top. Q equals MLF. And then after it's 0 degrees as a liquid, what does it still have to do, Sierra? Where does it have to get to?
Back to
I thought you raised your hand.
No,
What are you doing?
I was my hair.
Oh. So it started at negative 30, right? And it wants to end at 80. We've done this process so far. I want you to answer it. I know how to call it. We go from negative 30 to 0 as a temperature change. It then changes phases to all liquid at 0. But we want to get to 80. So what does it still have to do? Sierra?
Go to 50.
Where will it boil? When does water boil? What Celsius does water boil at? You don't remember? You should kind of know this by now.
100.
It boils at 100. So all it has to...
Yeah, okay.
Fahrenheit is 212.
Fahrenheit is 212, good. So it's never going to boil. So it just has to go from 0 to 80. So there's no phase change here. This is a temperature change again, okay? So you use this again. Now, take a look. I'm going to make some pointers. You can write these notes down if you'd like. Jot this down. Ready? This C is C for ice. This is C for water. They're different C values. C for ice and C for water are different. The change in temperature is how much here? Anybody? Change in temperature. What is it in the beginning? The first part, how much does the temperature change? 30. And then honor, this part? 80. So this is 30, this is 80. LF is in your table, C is in your table, the mass would be given. So you could find the total temperature change. You could find the total heat change. Heat change. And the heat change is the heat you need to add to the ice to get it to melt, pretty much. And get up to 80. Now, quick look at a calorimetry example. This is an example that your text talks about that you, I think, did in your homework. Actually, let me know if this is true. I think I give you homework with this problem. So you got a piece of iron and it's white hot. Okay, it's a white hot piece of iron, it's a specimen. You take this piece of iron and you submerge it in water. Why would you do that? To cool it down. So what's happening? The heat is moving from where to where? Very good. Here's the process, if you want to draw it, please. This is an exothermic reaction that's occurring. The heat is going from the iron, in the iron's case, for the water's case, it's endothermic, right? The heat is going from the iron to the water. So what's going to happen to the temperature of each of these substances? The iron temperature goes, the water temperature goes. Does that make sense physically? You understand that? If the temperature of one substance goes down, the other substance has to go up. There's nothing else that can happen. So if I want to know anything about this, I could just find the Q value of each and set them equal. So let's do Q for iron. Mass of the iron, C value of iron, times the change in temperature of iron. Well, what's the Q value of the water? All it is the mass of the water times the C value of water times the change in temperature of water. But what do we know because of conservation of energy? Conservation of energy tells me what? Come on, people. Conservation of energy allows me to do what? At this point in time, Katie? Set them equal. The energy that the iron specimen loses in heat has to go to the water. We are assuming the water does not boil or start to quench. When water starts to boil and like steam comes off it real quick, we have to make that assumption, or else then we have phase change also. We'd have to think about ml. But we could set this from the water equal to this from the iron. And now we could solve for whatever unknown we want. It depends on what's given. You'd have to be given everything else except for one piece of info. So if I give you the mass of the iron, or let's say it's an unknown metal. How about that? The mass of the unknown metal, you could measure the temperature change of the unknown metal. You know the mass of water. You know the specific heat of water. You can measure the temperature change in the water. You could figure out what the C value is. If you could find the specific heat, I'm going to ask you on the test. I'll tell you now. I'll do something like this on the test. Find the specific heat of it, and then I'll give you a table. And from the table, you figure out which material it is. So it's unknown metal specimen. It's submerged in water. You know the temperature change of everything, the water and the unknown specimen. You know the specific heat of water. You know the mass of water. You know the mass of the specimen. You can figure out the specific heat of the specimen. From that table, you can figure out what material it actually is. You could say, oh, because this much energy was lost, or because the C value turns out to be whatever it is, I know that this is iron, or I know that this is steel, or this is copper, or whatever it may be. Right? This is calorimetry at its finest. This is the whole idea behind calorimetry.
How is the change in temperature given?
How is it given?
Yeah.
You'd have to be given initial and final. Okay? It really doesn't matter if you're given in Celsius or Kelvin, because C is measured in degrees Kelvin or degrees Celsius in the denominator.
And so you're given initial
Final minus initial.
for both the iron and the water, or is
Well, if you think about it, what would happen then? Final minus initial of water. The water's going to heat up, right?
Oh,
So it's going to be higher minus lower for water, but for the iron it's going to be, actually, yeah, for the iron it's going to be lower minus higher. So one of the sides will have a negative sign, one will have a positive. The reasoning behind that? One's exothermic, one is endothermic. So if you want to, honestly, if you want to make it simplify things, you can take the absolute value of the temperature change in both cases. Okay? If that confuses you at all. That's a good point to make there, Katie, because you get one positive and one negative on each side. You could simply say that the sum of these equals 0, right? You could say the sum of this plus this is equal to 0. You can make that your equation. Or you could say that one side equals negative the other side, mathematically. Or, again, simplify it by putting absolute value here. Okay, but the physical concept here should allow you to understand the mathematical part more, right? Any other questions about this test? Any last minute questions you may have? Oh, one thing we didn't talk about was laminar and turbulent flow. What's the difference there? This was in 9.2.
Who's gonna be on the test?
Actually, was it 9.3 or 9.2? 9.2 and I
It's
forget.
like only one of them follows the formula of A1V1 equals A2V2.
A1V1, A2V2 assumes it's laminar flow for sure, absolutely. But I'm asking, what's the real difference? Laminar flow means what? What kind of flow? What's the word you would use to describe laminar flow? Think about a stream that's flowing very lightly.
What was it? Without turbulence?
Yes.
It'd be like saying, if I'm not tall, I'm short. What's the definition of tall? Not short. You know what I mean? It's not, you're right, it is not turbulent, but more specifically, what's not turbulent mean? How about that? What is it? Not still. There's a word I use for
Uninterrupted.
laminar flow. What?
Uninterrupted.
Sure, that works. Predictable. Because the other laminar, turbulent flow is unpredictable. So it's been interrupted. So laminar flow is predictable, streamlined flow. Think about flow of like, water going in a channel. Or remember when some groups tested the inclined plane with a fluid, they had a barbecue sauce, and when it was like running down there very slowly, that'd be like laminar flow.
So that was
Turbulent
just a hard
flow.
worker.
Turbulent flow is flow where there are like eddy currents and these riptides because of objects that cause certain particles to interact with each other after the object. So think about like whitewater rafting, the white water, the rapids, they come from turbulent flow. Think about an airplane. The flow over the airfoils is turbulent, causing turbulence in the actual airplane, causing it to shake. What did we use? There's a certain number that is utilized, that is measured to see if a flow is turbulent or laminar. It was a classmate's name.
Oh, Reynolds.
The Reynolds number. Okay? The Reynolds number. If the Reynolds number is below a certain value, it's laminar flow. If it's above a certain value, it's turbulent flow. So we didn't do this though. But you calculate the Reynolds number to determine whether flow is turbulent or laminar. Okay, keep that in mind because we want to understand physically how we can understand a fluid's nature. An ideal fluid was defined as a fluid flowing with a laminar flow that is non-viscous and incompressible. Remember, viscosity or viscous fluids are having to do with like the nature of the fluid to flow past its surface. So like a viscous fluid would be like molasses or syrup we gave as an example. Okay, it's something that is not flowing very easily. There's a lot of shear stress in the fluid causing it to slow down. All right, sorry. So any last questions? I thought of that as I asked any questions. Anybody? All right, let's stop there.